recording. Now I'm just gonna move to check the screen again. All right, I'll go full screen. Okay, everything good. So now, the rest of today's lectures is about tracking technology. For those of you who are interested in this space, I think you might find interesting. For those of you who are not, it's okay. You can just kind of mindful of them. Okay, it may or may not make it into the exam. Generally, it's not. Yes. But you can have a good understanding, some basic understanding, always good. Okay, so you don't, at the very least, you don't say the wrong thing. Okay, so the first one here is Professor Ivan Sutherland. So he from MIT, so he went on to university, can't remember his university, but he's a pioneer in this space in the 60s. He has introduced the very first concept called ultimate display. Okay, so there was some nice article, I put it on there, Road to VR, that you can take a look. Essentially, it's a mechanical headset. Okay, so in this case here, you can see the image on the left here. So he wears some sort of early prototype for stereoscopics. Okay, he is academic, so he worked in the university. And this will give you a sense of what mechanical job look like. Okay, just a little hydraulic, they kind of stick in your head into the ceiling. Okay, and then you're able to walk around, not walk around. You kind of stepping in and out, like sitting on the chairs, standing in the same, relatively in the same location. But your head movement tracking based on that, okay, based on how you move your mechanical piece with attached to your headset. Um, if you can call that headset at that time. Remember, this is 60 in the 1960s, so it must be almost 60 years ago. The image that he see, it could be something like very simple like this, a wireframe of an object, okay, and then he has built a kind of controller as well that track within the tracking system, so he can manipulate like the wireframe. He can move the box here somewhere else. Things that we normally come nowadays become more natural. At that time, was very difficult. There's no computer vision, no electromagnetics that we're going to talk about. So the very first primitive one, a very first, but still accurate, but it's very limited range. It's this one. Okay, it's a mechanical, electromechanicals. Okay. So this one is my PhD supervisor. So he's Professor Tom Furness at the University of Washington. Before he joined university in 1989, he was a researcher at a Air Force Research Lab, Wright-Patterson. Okay, so his work is about head-mount display, but for military, for people who sit inside cockpit. Okay, so this was his concept. Okay, of course, remember this is also in the 60s. Okay, 60s, 70s. Okay. So the headset here. Okay, so if you watched kind of Hollywood movies, so nowadays the technologies are far past this point. But at that time, everything is still manual. But they were talking about every component inside the inside the cockpit, fighter cockpit. Most in this case, it has many instruments. Okay, however, people are not able. It requires a lot of training and skill to be able to manipulate all these subcomponents together. Like for example, aiming a target, putting a target, putting some kind of missile on the target. It become a very difficult skill. So what his work was, he basically built it inside the helmet. Okay, so the helmet is actually where you're looking instead of you looking at the console in front of you. Okay, and you try to aim the target that way. You might have seen in the older movie, in how people aim at it. But now with the smart missile and everything, so the head mount display with the connecting piece. So it's allow you to track how your head is moving, and your target coordinate system lay on top of you. So it's not just you try to reorient yourself to the display in front of you. The display is actually get to try to reorient the side, the boring, the ball size of this thing right in front of your visor. So that means you move your head to the left, your target should relatively stay. It will stay at the same location in the physical space, and that it become an early concept of augmented reality. Okay, so even though the application are quite military oriented, but that's a very down bare bone. It's both of them, even Sutherland and Tom Finnis, was a foundation provide that in the 60s. And of course, now people are still talking about his technology. So that's what at that time was the one headset. So it moved into a little bit of military. So which is now still continue to do that. They now it's not just for this. It's all for combat training, ground force, not just in the cockpit anymore. There are quite a lot of that. So now VR and AR is quite expensive in this space in the military side. So, but in terms of tracking part here, okay, so we'll talk about some of the technology here. First one called optical tracking. Okay, so this is what one of the commercial product that are available. We have one. We bought this one in that we use in the lab up here in Newnham. Essentially, optical here is like a LED type. Okay, so the LED here you can see here. It use LED. It's red on the infrared spectrum. Okay, there are a little small red dot here. In the middle, there's an infrared camera. Okay, that looks. There's a couple of these attached to the ceiling. Remember the big wall at the University of Illinois that I showed you before, or the big wall panels across, and there's a whole bunch of these things sit on top. So this is generating a lot of light. Okay, infrared light. They come to this object, but this object is actually a controller, but it has this retroreflective ball. Okay, remember that all the spatial AR is need a retroreflective ball for these to create a reflection, so the camera can see them. Okay, now the trick for this one is that it's a solve multi-dimensional equation. Okay, so this one is basically how would you tell the distance and their orientation? How do you tell X, Y, Z? How do you tell their 3D orientation? So by that, it's actually for each one of these dots, the camera can see, okay, where this dot is in the camera frame, pixels frame. Okay, but since you have multiple of these, you can see the same dot from multiple angle. Okay, from multiple angle. In that case, you can triangulate location of it. That's a kind of simple nutshell the way people do the way this technique is done. However, you might wondering, how about this other dot in other area? Okay, that's where you're solving the equation, because if you just see a dot, you're only going to know where the distance are, but you won't know how they're oriented. Okay, so therefore there's multiple dots are now, but you will wonder how computer or camera tell the difference which one is which one. No, it cannot. What it can is actually is no configuration of this setting like this. It know before time that okay, this dot is precisely how much it's oriented among themselves, where they are precise physical configuration of that target. It's you can think of this like a image target for Fourier, but this one is a mechanical target that you have to tell the system beforehand. Okay, so that means that there's quite a lot of computation that normally a dedicated computer to run, get the feedback from these, getting feedback from multiple cameras. So you need two at least, but the system should have, depend on your field of coverage, how big they are. So I would say the big wall that we have 4 of them. So they can run off these multiple objects. So you can have a whole object treat like a physical mouse, or you can tie some of these to your body and then creating some motion capture. Okay, which is the School of Health here has that kind of motion tracking system, which is I think that's what Hollywood is using also. Okay, you will see this little dot everything inside the animation. So that's basically optical. It's light, has to do with light. Okay, so this one is a very unfortunately I won't be able to transfer the. But this guy, Johnny Lee, so now he worked for Google. At that time, he was a PhD student at University of Illinois, not Illinois, Carnegie Mellon, up in Pittsburgh, I think. CMU. Okay, so in this case, what he would demonstrate the very concept. Okay, early days, in 10 years ago, there was a V remote. So he just convert that into a simple homemade optical tracking system. I'm just gonna try to get to the part in which, oh, sorry. So what he will try to do here, what his demo really tried to do here, because you try to create a single point, but make them look like you're looking at a 3D image. Okay, so I'm just gonna fast forward since you can't hear him native. This just his setup. Okay, so you can see here, this is from the view that he showed. You can kind of get a sense that, oh, this would look like perspective view. Okay. But essentially, he was playing around. It's a 2D screen, but he using his the camera tracking system here to basically simulate that. So that means that as he moves his camera, that's a calculated position, which is based on this optical hat of the remote V to generate the few optical tracking. So basically, the camera that's moving around is being tracked at all time. Okay. So in this case, you can see here, you can get a sense that you're moving around, looking at different perspective. Of course, the image is not stereoscopic, but you can see the 3D perspective of that. So in and out as if you're actually there. So that's what's yeah. But remember the view that you see here from the third camera, which is not really being tracked. So that's why you see a little kind of out of perspective image. Okay. Because if you actually look from inside, you won't see this sort of moving around behind. So hopefully you get a sense of some optical tracking, cheaper, more expensive. Okay. So generally, the disadvantage is that it's very relatively accurate. Resolution of the light is relatively, you don't have a spatial resolution per se, so it's relatively good. Okay, so high refresh tracking system, high refresh rate. So that means that this thing could go very up to 100 frames per second really easily. Okay, disadvantage is sensitive to pollution. Okay, so in this case, of course, the light, if you get blocked, get shadow, get something, you won't see it. So I mean, that is what we call a line of sight problem. Okay, and oftentimes optical tracking system is really not easy. As you can see, the LED lights, you see to mount to the wall, need to calibrate, so it's not super easy to move. Okay, and you need to set up require reference points. Okay, so it's a calibration process that need quite a bit of work. Okay. So that's why people in academic particularly start to move into the marker-based video tracking. Probably around my colleagues, Mark Billinghurst has helped start this move. You will recognize some of the work here, which is a foundation that the Wuforias are built on later. Essentially, it's a marker, like you can treat them like a 2D markers, okay, that computer recognize. So now we're moving into computer vision now. So this is the late 90s. Computer vision, simple computer vision start to become available. Okay, so but the key here, remember, is a real time. You cannot track. You can track very accurately, but if it's a post processing, then you have no chance of applying that to the AR because the AR need to be able to track frame by frame. Otherwise, the latency will come. Okay, so that would be talk about. So AR, this is a kind of platform. So people train their system, their AR system, computer to recognize whatever pattern they shows. And then basically from there, then they just feed the camera in, looking for that frame, and then try to cut it out and try to see what their 6 degree of freedom look like, how far the card is, how closer the in a orientation perspectively. So that means you want to put a character there so that you know precisely how the character need to be oriented in the frame of display to appear to be on that marker. Okay. So that means as you rotate it, the marker wouldn't be kind of sit still. They will kind of move with the with the physical marker itself. Okay. So we call a marker. Okay. So that's what we have. So that's a little summarize people. Okay. And of course, you're more familiar with this one, Wuforia, so, which is now you probably go more than I think Ron showed you in a bit of demo last couple of weeks about the different type of target, not just the image target. Image targets was a simple thing by default. It's a 2D set like this, okay, and you have a virtual objects here. Okay, you can either move the card, okay, or you actually move your your mobile phone or your camera you're looking at. So and then you get effects of whatever that place augmentations look like. Okay, so hopefully you get a bit of sense of that. Okay. Now, I think this one is a founding work, breakthrough work, I would say. It's a best paper award at the top conference, ISMA, in 13 years ago. The breakthrough, what we call markerless. Okay, at that time we call markerless. Some people call natural feature tracking. Okay, it's basically the idea was really different than the previous one. Previous ones worked. Okay, you put a marker. I shown you a lot of past project that has marker there in the library on the shelf. As long as you see that, then the whole thing know what they're supposed to do. Of course, there's a limitation. That's the obvious one. So now people in computer vision area are really looking, and this is a work called PTAM, parallel tracking and mapping. It's a work that modify, that adopt the concept of what SLAM, simultaneously um, localization and mapping, SLAM, into this AR. Okay, the problem is the author George is not the first one to adopt this. However, before the adoption was not successful because the frame rate is down to maybe 1 frame to 2 frames per second, or if using a SLAM to run this. So essentially, it finds the feature from the environment. Okay, that's what the little color dot here is. So usually the feature here defined depend on your algorithm you use. So in this case, they use the age detection. So the age of the object. So that could be the age of the letter that you use on the keyboard. Or it could be the age of the tile that you have. So anything that creating kind of sharp angles of some sort of a contrast movement of image. Okay. So in this case, I'll give you a bit of a demo tour for the first. This is showcase the tracking. Okay, so this work is the first one that be able to bring it up to 15 or closer to 20 frames per second. You can see here the plane demonstrate the green plane is demonstrating the stabilization of the plane. And you can see the dot here. As they move to the new environment, they're picking up new color dot. Okay, just forget about the color. Just ignore that. So you can see here all those features are sitting inside using computer vision, run all the tracking all the time. Just try able to stabilize or not. All you have to look is the green plane. Okay, it stay there as appear to be there. It never moves. So that means the tracking is solid. Okay. So you can put a virtual content, put things like that. Yes, you can see. But this is showing that they can actually do a lot of tracking. That if you're running 1 or 2 frames per second, you will not be able to move the camera this fast, and the green grid would not be able to stay there as it is. So this one to demonstrate the case, okay, of how to do the scale. Okay, so that means this is a classic problem at a time. So you in the small space, yeah, you track, you have animation. So what it would look like is that generally people have difficult time of when you actually move further away from the tracking that you start with, and you basically your model. You right now pay attention to the model. Model is doesn't really lose registration. You can move your head around. You can come very further out now, and then you can go very closer. Okay, so that means that it shows robustness of the tracking. That's a key problem with this kind of tracking because you don't really have a marker to depend on. So that means that you want to show that actually there's a lot of tracking capability. I think this one is, you don't need this, see this one. I'll show you this. Okay, so this one to show you the really the ability that this is the beginning. So mapping, go here. And then this is really show it's a game, but it's really, you see the plane, the grid plane, green grid plane is gone, but then you can see all these characters, Star Wars characters are really in on the table because he put the grid on the table. Yeah. What this video really shows is the speed. Okay. Even though the frame rate is probably just like the what video recording is about 30 frame 29. Okay. But that is actually unheard of at that time. Okay. The reason I point to this work, we are linked to that later on. A lot of these work is actually foundation of what AR and VR technologies are using at the moment. The guy here just went on to work for the Microsoft, for the one that's running the HoloLens. Okay. And you can see here that all these things. So you can see here the stabilization. You have to see all this dead character. They don't move around. If there's a registration problem, then that they will not be aligned where they aligned before. Okay, so this is a kind of a starting to be a kind of components. but it's still a difficulty. Okay, there's a difficulty in this kind of thing. The frame rate is still relatively small. Okay, low, not small, like under 30. So therefore, for commercial use, it's a little bit limited. So people will start to still keep looking for that point. What's the better way to do it? Which I'll talk about that shortly. But now there was in parallel, there was a technology that kind of ubiquitous. You've seen it's everywhere, inertial sensor. So that's this measure based on the gravities and how people move, things, acceleration, gyroscope, and they're everywhere. So in your phone, in a remote V sensor, there's all this micro fabrications device. It is actually available everywhere. Okay, so it's just a measure inertial. Okay. So in the phone, you have that to rotating for accelerometers, direction, how you move. You can see you change orientation of the phone and the screen keep changing. So that's the accelerometers stuff. We should detect the sense of where the gravity is and where it's not directions. Usually it's compiled with 3-axis accelerometer, X, Y, Z, that align with physical phone directions, just like the arrow in green, blue, and red. And then it depends on how the phone is oriented in the real world or against in the frame of reference of gravity. All this work is basically induced. Okay, so let's say the phone is really flat, the green really put it on on the floor or on the table. So the blue one here, the blue arrow axis here, okay, will get the accelerometer read that okay, you have 1g, which is 1 gravity Earth, okay, and the other gets 0. So that if that's the case, the system can process that your phone is sitting straight. Okay? If you're tilted, then of course in whatever direction the green could have some reading that has some gravity g there. Okay? So those are kind of basic principle approach of those accelerometers of those inertial devices. Initial tracking here is a very disadvantage, quite handy. Okay, it's a micro MEMS device, very very small, tiny, as I said before, anywhere, and it requires no reference. So that means that there's no frame, there's no calibration, or there was if you use um, uh, the gravity. I think sometimes you have to perform resetting, moving as an 8 number around the magnetic Earth. Referenceless, okay, generally. So no, not sensitive occlusion. So you can track this. There's no source. There's no emitter light. There's nothing receiver. It's just by itself. Okay, and very small size, I said before. And it basically could be wireless IoT device. It's now use a lot of this thing. Okay, and it's one big plus is update rate. Okay, that's 1,000 hertz easily. When optical can be really about 100 to 100 at most. Okay. The disadvantage, of course, it has a problem we call drift problem, which is inertia alone will have since it doesn't have a reference, it doesn't have the tracker, it doesn't have the marker. So what it does, it calculates by itself. So by itself, it detects accelerometer, which is acceleration. So in order for you to actually calculate the placement, you have to perform mathematical operation called double integration. Okay, so what that means is that whatever noise you have accelerometer usually accumulate into a drift noise. So that means that if you have the tracking the based purely on inertial, and you look straight, and you rotate your sensor around 360 and come back to the same place, the sensor will report slightly off, okay, 360 degree when it should have tell you precisely 360 degree come back. Okay, so what that means is that every time you do this, or every time over time, every update like 1,000 hertz here, it would have error that start to accumulating based on that double integration. So therefore, your drifting could be like your head may not move at all, but you've been wearing the system and the tracking system and running for some few minutes. You end up having this position kind of slowly drifting off, even though the sensor might just not never move. It's just placed on the ground, or placed on the table, or don't touch, but you will appear to that. If you use this kind of thing by itself, that's what you're going to have. So if you put that in the drive, the headset, you will see your scene kind of drift off, like as you are slowly moving away in certain direction. So that is one main issues. Okay. So other tracking technology, acoustics, this one is a startup for opticals expensive, so people use style. Okay, it's a similar concept with similar concept with the optical that I showed you before, but this one you use sound. The occlusion problem is less a problem. Okay, because sound can go around. However, this acoustic has some issues in light, a little bit of still a light of size is still issues, so you cannot really go through a brick wall. Environment change, that's a big problem with the temperature because that change the way sound travel or speed of sound travel. And that is very important for calculating the space. So you need to know for the light, as we all know, the light is fixed, light speed is fixed. So that means that's one thing that you can count on, but this one you cannot. So therefore you end up with a low accuracy, low resolution. So that's why this is not one of those popular ones. This one is actually used in the early days for the special effect, okay, magnetics tracking. So that one you put a lot of components in there attached to the suit, motion capture suit, but now they all move to opticals. Okay, so this one electromagnetic, similar things. So you send out electromagnetic wave in three-dimensional plane view, and then you have this receiver in three-dimensional sitting there like an antenna attacking it, similar to gyro accelerometer three-axis. So this one has similar thing, but they're picking up, instead of picking up gravity of the Earth, they're picking up magnetic field. Okay, which is quite handy. The problem with this one is the advantage is quite significant. Okay, it's expensive, but it has high update rate. The disadvantage, the major one, is a magnetic interference. So that means that the field here, if you are someone, when you're running it, if someone walk in with a large metal object, so like a piece of ply or metal that you put in there, it creating it's just like a magnetic interference, because the magnetic that you send out from the tracker, from the emitters, from the tracking system, is react to this object. That's what electromagnetics and creating a different view of reflection. So therefore, when you read the reflection out from the receiver, it's difficult to determine. It become interfere. Okay, so therefore you need to do recalibration for that space again if the object magnetics metallic object happen to be there without unaccounted for before. Okay, so that's why this one is not one of those. It's one of those that not that popular nowadays. And of course, this one we use it every day now. So compass. This is particularly useful for the early AR process. It's basically direction you are and direction where you're going. So that's more important, more relevant to outdoor AR, augmented reality. Like Pokemon Go use quite a bit of these. Okay, to try to tell okay where you are in space. Okay, and of course in the outdoor AR, a lot of them using GPS, a global position system, which is all this using for all Google, all the maps and everything, navigation. So you can see here the idea here, you have a center point, which is a little blue dot there, that actually every satellite visible can give you a code that unique for that satellite. Okay, and then you yourself, it's actually going to calculate where you are based on the signal that you receive from the GPS, which is a perfect, quite handy for the AR outdoor, for the outdoor that you're required to see where you are. So having said that, comparison of tracking technologies, as you can see here, so it's quite a pro and con. There's really no, I'd say no win-win. There's no number one choice. They always prefer and more updated things like that. So that's why people are more moving closer to what we call a hybrid solution, so tracking. So this is the early version by Navy from the US research that I will participate in. So you can see here, there's a orientation tracker, there's GPS, there's a camera, there's a display, and there's also a GPS pad computer, portable, and you can see that's really portable. And there's from the Cambridge University, there's another portable version that built with IMU, inertial measurement unit, as a sensor and camera. So all these people 15 years ago were really pushing this one to kind of be okay, because different individual technologies are not really adequate. So people are looking at that. A lot of these including my PhD thesis, I use some of these as well. I use hybrid, but the whole thing was based on algorithms. Okay, so the algorithm here, how to view the data from different sensors, sensor from inertial sensor, from camera. How will you know how will you know how to combine them? So that's the algorithm. So people use Kalman filter, like my thesis, PhD thesis, and things like that. So kind of sit in there, which is a research. But it's a very good timing because nowadays those things are no longer in research university because now become available in the hand of your phone, like Google AR Core, okay, that you play, and that Ron is showing off, all those things. Even though it looked like it based on the camera tracking, but in fact no, it's actually use magnetometer, use a accelerometer, gyroscope, use a camera. So this is really quite a lot of tracking that AR Core integrated. That's why initially when it came out, it only available on Google phone, Pixel phones, but nowadays it's getting more better because most of the phone has similar hardware now. So that means it's not just purely looking using the camera. Okay, it's actually looking at other inertial sensors as well. So that means at the core of it, it would have a chip, the algorithm that determines this specifically. Okay. Another term that interesting that you might find if you want to dig deeper into this called visual odometry. Okay, so that's a bit robotic view, but you can get a sense of that. So it uses a visual, try to find location itself. But for AR interface people like myself, we are using to determine our viewpoint. But for robotics, they use that to determine the map of the area that they try to map. Like go into the warehouse, unknown things for safety reason, things like that. So those terms are more applicable visual odometry. And of course, we didn't have a chance to play. It's a similar technology called AR Kit. So that's it on iPhone only, on Apple Cam, but the core and the bottom is the same. So that means it's kind of give you the evidence that this technology are here to stay because the two major phone company are really using it. Yeah. And then this is what we have for the Oculus. Okay, you might wondering how they track itself. Okay, so hopefully after listening to my lecture today, you get a bit more kind of questions. Well, how exactly? So underneath the hood of Oculus here, okay, so on the old types, so you have a kind of tractor boom that sit on the table looking at you. In that case, they are looking at this LED light. They should sit underneath the surface that you see here. You can't see with your bare eye here. But when you turn it on, you can see them kind of illuminated from the from the inside. Okay, so and that's the same thing with the optical tracking that I showed you before with the line of sights and those kind of things. In this case, is that either you have an external sensor looking at this and you see a reflection in this, or you actually have a camera. And in the new Oculus headsets, they all has a camera outward looking, so those camera are looking at those reflection light. Okay, so oh sorry. So that means that you will see the movement. Oh, actually, I should show you this. I have the video come up already. Okay. All right, so let's see. This is a movement, okay? And you can see here, the movement from the sensor point, it can tell you which one is lighting, okay? The number here specifically to the which part of the headset they were looking at. Yeah. That's the same thing with the retro reflector in the optical tracking that I showed you before, will weird shape, okay? In this case, they know precisely what the headset look like as far as where the constellation or location of those sensors are. They just need to know which one they were looking at. Yeah. So hopefully you get the sense of that. So that means that in the current mode that we're using, okay, no external sensor on the ground now. If you come to the practical, it's just a headset because the headset has a camera. Like Oculus Quest has a camera, 4 of them looking out. So they just look everywhere, not just look. Think about it. This is a combination. Okay, they're not only looking at the handset, so they will see something like this. These are 2 handsets from the camera, from the headset. They would basically not tracking from external. They're tracking from the head itself. So that means that if you move your hand controller to the back of the headset, you won't be able to see it. The hand tracking won't be able to see it. All right. So that's a trade-off. Okay. But I think that's turned out to be not a big deal. But however, the camera is also looking. Remember those little thousands of dots floating around with using the Star Wars character. Those are natural feature tracking. That is what the camera is looking as well. Looking at the space, looking at the object, looking at everything that they happen to see it. All right. So um, the technology had goes so much from that video before. Is that before it was the scene change. For example, if you track the keyboard, if someone moved the keyboard in the middle of run, you will have problem because they expect to see something, and the map that the system created is not be able to match with what they see. So that could creating a problem in their resolving in their triangulation. But in this case, the algorithm is actually accommodate all those changing occlusions and something move out and things like that quite well. So if you come and have a play with the Quest, you will get a sense of that. So that is one thing. Okay. Another thing that roll out with this hybrid approach before was HoloLens. Okay. So this HoloLens is relatively this one is an older version, but in the newer version is similar. Okay, so you can see here there's a depth sensor here that basically by itself is can see where each of the pixel inside a camera, which the distance are they. Okay, so you have a color video, so you have a long range infrared ray, grayscale camera. Grayscale camera is what the guy was showing you the breakthrough in 2017, the PTAM is using. Basically, he was basically use that to basically find where location the headsets are by looking just a feature in front of them. Okay, so that's quite a number of this information. This is we only talk about tracking, but there's another holographic chip in here that render the holographic display. Okay, so that's another components that important for HoloLens. So that you can see here a lot of technologies are very early age that I show you, and then now it's merging maturely into some of these commercial product. Now, beyond positioning tracking, okay, so there's other things like this control. So this is a cheaper version, but there's expensive. You can go to the website, you can look at them. Essentially here is looking electronics, basically the signal that generate by your brain, and try to interpret that and what your intention is. Okay, the implication of this is quite useful for people in handicap or people who are paralyzed, so they might be able one day able to actually transmit their brainwave that's still working to be a communicatable cue. Okay, so this is just a little bit early in the early days. Okay, but of course, if you're Elon Musk, he was doing SpaceX, and he also has this brain-computer interface unit that he showed off a few weeks ago. Okay, that one day he might be able to plant some sensor inside a patient brain, able for them to communicate, and also might go in control the artificial limbs. Okay, so this is really going to be a next breakthrough. It is actually you're going to have a more for disability and handicap, and hopefully and also have a more on advanced computing components. This one is the startup, okay, which is didn't quite go really well. It basically is different than you're using optical inertial. This one is quite interesting. The armband is actually detecting electronic signal that created by your muscle. Okay, and you can see here that will show the basic. So every time you move there, each channel here detect different muscle move, not muscle movement, electricity that create inside your muscle. Okay. It's limited to quite a limited range of interaction, yeah. Tilted, left, right, things like that. But as similar to other interface technology startup, it always has a good to start. Okay, very nice, cool demos. But the company, of course, been around for at least 5 years. So I don't think they make it commercially. Okay. There's a limitation in what technology can do. Okay, but it's a concept in terms of sensing device is actually quite interesting. Okay. So this one is, I talk about that, so I will go really quickly on TUI, so you can see different things here. Okay, so I think you talk about the object, combine the objects. So think about it. It's important that you are, when you look at the Wuforia, it's actually you should see something like this, because Wuforia should be print out. You should think about be able to print them out inside a kind of piece of marker or like a piece of paper that had camera or mobile phone interact with. So that is more what intention is. I think Ron showed you the cube one, the one with the creating a cube target, okay, not just an image from. So that's become look like a tangible component. So just make sure you try to think of it that way. And we have this before. This is also in early days of moving platform. We talked about this in teleportation before in previous lecture. So you can see here that people have to build them from scratch. So this is back in the hit lab in 20 years ago. And this one we show you before virtual sphere, but I think I have the video here. With the portable VR headset, this kind of thing would be quite handy. At that time, they have to work out quite an engineering solution to make sure that display work, and then they have a wireless transmitting of the RGB sensor of the video to go in. There's a view inside. Okay. But of course, it's a little bit need a little bit of space. Okay, so you need a bit. I think about at least 8 to 10 meters to be able to put this cache. And I think I mentioned this before, is that the way you rotate is not natural, because all this is moving using your just skateboard view. That means everything in here with the mass of this 100 kilo or so, I guess, is to change rotation quickly is difficult. Okay. Sometimes you could fall over there, and then even you fall over, you might not be able to stop the view, because there's no control component here. We just keep moving, just like you fall off your skateboard. Of course, they will drag you up. They'll continue to go. Okay. And of course, this one is more modern. Okay, hoping to get, but it's super expensive, so it requires special shoes. Okay. Let me just fast forward to the shoe part a little bit. Okay. Yep. So you can see here the shoe, underneath the shoe has a little knob that actually go to this each one of these. So basically, they just allow you so that you can create a traction inside this. Okay. So that means you require special shoes type. Okay. But it's quite handy. In this case, you can change direction relatively easier. You don't need to overcome the inertial model of the sphere, big sphere heavy. The waist is linked you so that you can actually have a sense of stability. Okay. So that just gives you a sense. So this is all tracking. Okay. Now the holy grail, a lot of this for the actual head tracking is eye tracking controller. Okay. So this one is relatively far out, similar to the brain computing interface. Okay. So this one is actually has many technologies. Some of them are super expensive. We have a few of them here to detect just where the eye is. It's not just where my head is looking, but why exactly my eye is looking, in which corner, how my eye is rotating. Okay. So that one is generally use a technology that you put in some light that you can see the reflection that come out. And this is exploit side effect that you might have seen in an old photograph with the red eye. Okay, so that when the light goes straight to the back of your optical lens, your optical eyes, and then it come out. So it's basically you can see that. So nowadays the technology photographs that went past that. So but that's what eye tracking are using to track. So where your focus is, where your exit people, they call exit people, is where your center of your eyes is. Okay, that when you're moving around, as your eyes moving around. So, for example, in this case, it's a handy. So it's not just where your head is looking, because sometimes your head is not that move much, but your eye moves a lot. The difficulty for eye tracking is also very difficult. So in this case, it again come from the cockpit. So you can see here the head is looking relatively front forward, okay, but your eye is actually can be anywhere. It could be on a console, could be on a target, could be on anything. So therefore, that is something that people are not quite get there, but they really want to. Okay, so some of these is something like this. So they try to get some portable, cheaper version, put them in a VR headset, something like that. So this is from one of our portable unit. Okay, the little blue here, little dot here. This is a live viewer camera. You will see this what they call a heat map. Basically, wherever you go, it's a center focus. Okay, if you stay there long enough, it will turn red. Okay, that dot will turn red. And you can see here, this is running. The headset is running. In this case, we are running some work that working on where people are looking at a package, packaging a beef apparently. And you can see the eye is there, still there. So they now they move. So this is where the study was focused on. It said if they look at a package of beef, where exactly are they looking on the package? Okay. See if we can scroll it up a little bit there. Yep. So that, remember the red one mean that's where people are looking at most of the time. But of course, in this case, the experiment was the testing. Normally, the package will not be able to move because you're not tracking the package. Okay, so that's why the map is not there. So that means the package is fixed. So you just have to focus. Your head can be moving around, but your eye will actually try to stay focused in some area. And that's when, for marketing part, for this particular study, we'll try to determine where exactly on the label that people are looking at. Okay, but this is just a mock-up case to show you the capability of that. All right, so hopefully you get a sense of that. Okay, that would be the end today. So let